Greetings. In this video on abstract algebra, I'll be talking about groups of permutations. So, what is meant by this in general idea? And this will be a short intro in a basic context. It won't be going deep into proofs of individual properties, the fact that these permutated functions indeed form a group together, like the proof of all things, will kind of be shown implicitly but not necessarily explicitly via explicit proof. But what I'm talking about here is groups of permutations. And this is a very important phenomena in abstract algebra, and it is in simple terms as follows. One gets bijective functions, which means basically one input is mapped onto exactly one output, just like one output will only come from one input. That means that no two outputs will be linked to one same output. What it means in the sense of sets is there's set, let's say set containing A1, A2, A3, A4, set A, and then the function maps it, this bijective function, it maps it onto another set with four, also the same amount of elements, B. And what it means is that one element will only be linked to one element in the other one. So the one input from A will only be linked to one input in B. And how it's end up? That all the A elements are taken up for at least and at most at the same time one output inside B. I could, for example, do it like this. A1 goes to B1, A2 goes to B2, A3 goes to B3, and A4 goes to B4. And this function can be denoted in this matrix form. This is a matrix form that I'll be using for this idea of group of permutations. And I'll say that this is, let's say, the function f. So I will define this f to be basically for A1, it will go to B1. For A2, it goes to, as follows. For inputs A1, A2, A3, A4. So this is the set of inputs, and as I said, bijective function. So exactly the same amount of inputs, outputs, B1, B2, B3, B4. And one is linked to the one written below it. So A1 goes to B1, A2 goes to B2, A3 goes to B3, A4 goes to B4. And it means that it won't, what can change is the order of these four. Alright? So one theoretically can say that these are set, these are also set, but the order in which they are linked is can be changed as a result of permutations. And of course, not both A's and B's have to be interchanged as far as linear position at the same time. One can just interchange the position of the B1s and get all the combinations of all the permutations of or the combinations of different individual elements from the A and B set, and one sees their same amount, and each has one output inside the B set, only one, at most and at least one connected element that is corresponding to it according to this function. So what I'll now do is basically go to a more concrete example. This was abstract, and we're still working with abstract algebra, but nevertheless, I will show this with a concrete example of, let's say, this bijective function 1, 2, 3 being the inputs, and the idea of permutations will be basically I'll take the same values, but I will reorganize them in all possible ways, in all permutation ways, or in all ways they are results of different permutations that it can be put into. So of course, I have these three numbers, 1, 2, 3, three elements. Well, this will be the set from which it comes, the input set, and this must be bijective function as I had said before. And let's say the first option is that 1, 2, 3 will be linked exactly the same way, that this will be basically the identity function. That if this is mixed with another function of similar, another bijective function where these three are exchanged, it won't change the result in combination with another function in function composition. But that will be shown in a second. Well, I'll show that in a second. But the point is, I will say f is 1, 2, 3 going to 1 going to 1, 2 going to 2, 3 going to 3. What that means is f of 1 will be 1, f of 2 will be 2, and f of 3 will be 3. That's the point. And now group of permutations will be all the possible f. So let me say this is f1, f2, f3, f4, and so on, such that always 1, 2, 3 are the inputs, 1, 2, 3, 1, 2, 3. But these three numbers are in a different order. So hence the permutations. This 1, 2, 3 at the top, 1, 2, 3, 1, 2, 3 will be in the inputs, but for the 1 it can be, instead of 1 it can be 2, and therefore now there's 1 and 3 left for these two. So the permutations, one can find all the possible options. So let me exchange these two, so 1, 3, 2. Then another thing one can do is exchange these first two, so 2, 1, 3. Then one can exchange the first one and the last one, so 3, 2, 1. And one can check if all combinations have been used, but actually one can check it the way that one can see, okay, so there's three numbers, and I talk about these bijective functions that I'm, first of all, for example, working with the simplest one. I have three numbers linked to the same results as they are themselves via this bijective function f1, but then these outputs, I will just reorganize the order in which they are. Take different permutations of the output set. Basically the set doesn't change, but what changes is the order of the bijection which values are according to are connected to which inputs. Then this is first order organization, with the first one still being 1, so 2, 3 and 3, 2. Then let's look at those that have the first number as 2. We have 2, 1, 3, but another option is 2, 3, 1. So that was forgotten. So F5, let's say F5 is 2, 2, 3, 1 on the bottom. 1, 2, 3 still on the top. Alright, so 2, 3, 1, 2, 1, 3. And then 3, there's just one beginning with 3 on the bottom, so F6 will be the last option. 3, 2, 1, then I will do 3, 1, 2. 3, 1, 2. 1, 2, 3. So these are all the functions inside the group of permutations of this 1, 2, 3 function, with this being 1, 2, 3, then it being 1, 3, 2, 2, 1, 3, 3, 2, 1. So this is concrete example of group of permutations. What's interesting about this is that one can now look at different properties. And group of permutations, by default, a group, it has, of course, its elements. So these are the elements. It's basically one, for this example, as is seen, 1, 2, 3 are the input values. 1, 2, 3 are also the output ones, but in the output they are reorganized. So of course, one can be according to 1, 2 to 2, 3 to 3, but it can also be in this way that at least one will be exchanged. So that means 2 will actually be exchanged. 2 to 3 and 3 to 2 instead. Or 2 to 1 and 3 to 3. Or 2 to 2 and 3 to 1. All these options, because there's three numbers, there's now six different permutations. So that's the reason why it's called the group of permutations. Now, the idea here is that this group, it has its elements, and also as a group it has its preset, or it has its operation, and the operation is the composition, function composition. So the operation is function composition. And now for a group to be proven to be a group, it has to have identity working for both directions. It has to have with the order working in both directions. It has to have identity element, which it has, as I had actually mentioned in the beginning. The identity will be this function that assigns the same outputs as the inputs are. So this bijection 1 to 1, 2 to 2, 3 to 3, one element to the same other element for all the elements in this bijective function. And so for the kind of operation it has to have this identity, which is this identity kind of function. The inverse, well, one can find the inverse. Also, the order can be found. The order is the amount of times a function has to be put into an element of the group has to be put into operation with itself until it reaches the identity element. And the identity element, well, for each of these we can try to put this function into composition with itself, right? And find how many times it takes until we get into the identity element that will be the order of that concrete element. So each of these functions is elements of the group. So that means these six functions, these six possible permutations are they're called permutations in general, are the elements of the set of the group. And and all the group properties are satisfied. As I said, this was mentioned implicitly. It can be also shown via proof in an explicit manner. Now, to just show or illustrate what the point is, what is meant by the operation of this group being function composition, it is meant that one takes one of these functions and puts them into composition with another. So f1 in composition with f2, it basically means that one has this input value, and the input values, just this also makes it simpler, are always shown in the same order. And instead of putting it straight into f1, one first looks for what f2 gives it, and then one puts that value into f1. Now f1, as a matter of being this identity function, the same outputs as inputs, maybe for a nicer example, we could rather look at f3, f2. So let's say f2 and f3. So basically, this composition, function composition. Well, what that gives is basically, I can also write it as follows: 1, 2, 1, 2, 3, 1, 3, 2. Like this in composition with f3 is 1, 2, 3 again, 1, 2, 3, but then one goes to 2. 2 goes to 1 and 3 goes to 3. That's slightly different. Now, how this composition works? Well, what I'm looking for is a third function, and it must be member of the same group of the same set of these permutations. Why? Because a group, it has to have closed operation. So the operation must give an element that is still element of the same group. And you know, with all these permutations, what can happen when one puts into this function composition two of these permutated functions? Again, it will be a bijective function. Composition of two bijective functions will be bijective, and also it will have the same input values, and it could only have one of these just different permutations of the output. So again, by definition, or this is like implicit proof, it can be proven even lengthily, more space, and not going to do it now. But in any case, result of any operation on this group, where the operation is composition of functions, composition of any of these two functions will again give, as a result, one of these functions. Alright? So inside a group of permutations, when one puts these elements, hence these permutations, hence these individual functions, in composition with each other, it doesn't matter how many in a row, always the result of that operation, or that chain operation, will be again one of these 6 functions in this case. Or if there's more functions in another group of permutations, when it has more elements already in the inputs set, and therefore it has more different permutation options, then of course it can be any of those group's elements. And in this case, we have a finite group with finite amount of elements. So we know that even if we take composition of f2 and f3, the result will be something on the same group. So what will be the composition of f2 and f3, just to show this? Well, how it works is, again, f3 is like f2 of f3. So it's like f2 of f3. One can say that the argument of it is the f3. So what I input is always this upper row. That's the notation of this kind of function, the discrete bijective functions. So basically the idea is as follows. If I want to do f2 on f2 of f3, what I say is, okay, so what does it give me for 1? Well, I will first look what this function, so the f3, so the one on the right, this is the usual order the composition is taken in. So that the one on the right will be put inside the one on the left. That means, okay, so what this one takes me in the right one, in the one that's inside in the f3, well, f3 will take me to 2 on 1, right? So what I have to do now is go back to the f2 and look what f2 now gives me for 2, that's 3. So therefore 1 will give 3 in the composition. The result will be another permutation, another of these functions, and might be one of the 2 that I put inside, or might be another one of the 6. So one gave 2 on the second one, that is argument because composition, and then I go back and it gives 3. The same will be done with 2. So 2, well, I first look what it gives on the second one, gives 1, 1 gives 1, so it's 1 here. And for 3, what gives 3 on the right one? Well, how I can do it is, of course, always go from the right side. So look, 1 gives 2, therefore I will put it here. So 2 gives 1, 2 gives 3, therefore I put 3 here. 2 gives 1, therefore I go here to 1, 1 gives 1, 1 here. 3 gives 3, 3 gives 2 here, so it's 2. So I see that the composition of f2 and f3 is equal to 3, 1, 2, and that is f6. So F6 is the composition on the group, or in the group of permutations, the operation between F2 and F3, because we define the operation to be function composition, is the function I denoted as F6 in the beginning. Of course, the order of these permutations doesn't follow any necessary pattern or any pre-meant pattern in advance, but it simply is one of the elements. So again, this has shown that putting any of these 6 functions together into operation, where the operation is the function composition, will again give element of the same group of these groups of permutations. So this is the idea here, that we have such functions, and what one can find is such facts. And now what we might do in the next video is also look at, let's say, finding the order or exploring other notations for this kind of phenomenon.